Good afternoon. My name is Francis Baek, a research associate at the University of Michigan and an incoming assistant professor at Georgia Tech starting from this August. Today, I'll talk about our recent work, personalized emotion adaptive robot control strategy for human-robot collaboration in construction. I hope you enjoy it. Then let's get it started. As robotic systems have been emerging, there will be both humans and robots closely working together within shared workspace for shared goals. Robots are expected to take over physical, repetitive, and dangerous tasks for humans to focus on intellectual, dexterous, and supervisory tasks. Such human-robot collaboration holds great potential to alleviate many ongoing issues, such as stagnant productivity, safety risk, and labor shortage. In order to realize those great potential, primary focus has been on advancing robotic capabilities, such as improving robot precision and autonomy levels, which have made strong strides. But this may not be enough as we do not consider how humans will respond to robots. If robots can make humans to feel more concern, more workload, but reduce trust, humans can become less productive and may try to avoid robots, which can have negative impacts on this teamwork. So despite the great potential, without considering human responses, we still cannot assure if these human-robot teams can overcome these challenges, or rather introduce new challenges. Particularly, considering emotional responses can be crucial, as emotions can affect the overall performance in human-robot teams by influencing various factors of workers, such as decision-making, mental health, and acceptance of robots. So if robots can adapt to these emotional responses in ways to foster desired impact, such as improving decision-making, improving mental health and acceptance of robots, this can lead to maximizing the great potential of these human-robot teams. However, enabling robots to adapt to emotional responses is not straightforward. Recent technologies, particularly reinforcement learning, have enabled robot adaptation even to complicated environments. However, robots are typically designed to take one-size-fits-all actions for anyone at any time. For example, a robot will always slow down if someone feels bad emotions, but this may not be effective for everyone if someone has different feelings or preferences. So we may need personalized robot behaviors, but it is not straightforward as well, as the nature of human responses can violate some fundamental assumptions of reinforcement learning. For example, human responses are known to accumulate over time, can change over time, and can be different among individuals. This can break the Markov assumptions, and this can create non-stationary environment and limit the policy generalization. Also, training reinforcement learning generally requires a large numbers of interaction, in our case with human, but this may not be done easily due to safety-related or practical constraints. So we still lack an effective method for robots to be adapted to individuals' emotional responses. In order to address this issue, we propose a personalized emotion-adaptive robot control strategy. We assume that robots can monitor biosignals like EEG, referring to our brainwaves, using wearable biosensors. Then robot will take an action by adjusting parameters that are known to affect emotional responses, which are movement speed, arm swing speed, proximity to humans, level of autonomy, and leadership during collaboration. Then the corresponding changes in emotional responses will be modeled by analyzing these biosignals in terms of valence and arousal, which refer to feelings from displeasure to pleasure and feelings from relaxation to excitement, respectively. And these two are major constructs of emotion that can represent diverse emotional states, including happy, upset, or relaxed. So based on this modeling, the robot will plan its next action to foster happy emotion while pursuing high team productivity. And here, we especially focus on happy emotion, as it is known to enhance worker performance and acceptance of robots during human-robot collaboration. Then based on its planning, robot will take the next action, and this process will happen in iteration. To implement this strategy, we adopted model-based reinforcement learning using our prior knowledge. In our prior study, we established a regression model structure which captures how robotic parameters can affect individuals' valence and arousal. And this model structure reflects some fundamental nature of human responses, such as immediate changes and their potential variations over time. And its personalized coefficients allowed us to capture potentially different responses among individuals. So the robot embeds this model structure and only need to learn the personalized coefficients. And this enabled the personalized adaptation while achieving this learning process data efficient and stable. So as an early attempt to evaluate this strategy before testing it with real human participants, we simulated 1 hour of bricklaying task in a virtual environment with synthetically generated human workers. For 1 robot and 1 human team, a robot delivers brick, the human places it, then the robot brings another brick, and all which the robot monitors emotional responses and adjusts its parameters based on our strategy. And here, to generate the responses of 20 synthetic workers, we used the regression models from our prior study. So in response to robots' actions, these regression models estimate corresponding changes in individuals' emotional responses as if the robot is measuring them by analyzing biosignals. And these are sample robot behaviors with 5 synthetic workers. And as you can see from these different patterns, we can see that the robot took different actions for different workers, which demonstrated that our strategy enabled personalized robot behaviors. We also tested if our strategy could foster happy emotions, and we compared it to a baseline strategy, which focused only on maximizing the team productivity. And as you can see here, with this baseline strategy, only 5 out of 20 synthetic workers could feel the happy emotion, and the expected duration across workers was around 15 minutes. On the other hand, our strategy could increase that to 37 minutes on average, and now all 20 synthetic workers could feel the happy emotions. So these results demonstrate the potential effectiveness of our strategy in fostering desired emotional responses in workers during HRC. But we should also notice here that actually adapting to emotion may reduce some productivity. Here, the team productivity dropped from 314 bricks per team hour to 244, which may not always be acceptable in work environment. So these results also present the need for further analysis to figure out how we can achieve the better balance between fostering desired emotional responses and achieving high team productivity. And based on these findings, we are currently working on demonstrating our strategy with real human participants. So in this study, we proposed a robot control strategy, which enabled personalized behaviors adapting to individuals' emotional responses. And our results showed that our strategy could promote desired responses for all 20 synthetic workers. And at the same time, we could identify some potential trade-offs in productivity, which require further analysis to achieve the better balance between desired emotional responses and high team productivity. I appreciate all the great support from my collaborators and sponsor, and thank you for your attention.